Here I am waiting, I'll have to leave soon, why am I?
We're going to talk about functions and their properties, section 1.2. Mathematics and its applications abound with examples of formulas by which quantitative variables are related to each other. The language and notation of functions is ideal for that purpose. A function is actually a simple concept. If it weren't, history would have replaced it with a simpler one by now. Here's the definition. A function from a set D to a set R is a rule that assigns every element in the set D a unique element in set R. The set D of all input values is the domain of the function, and the set R of all the output values is the range of the function. Now, there are many ways to look at functions. One of the most intuitively helpful is the machine concept, in which values of the domain X are fed to the machine, which is the function, to produce range values, which is Y. To indicate that Y comes from the function acting on X, we use Euler's elegant function notation, Y equals f of X. Here, X is the independent variable, and Y would be the dependent variable. A function can also be viewed as a mapping of the elements of the domain onto the elements of the range. The figure shows a function that maps elements from the domain X onto elements of the range Y. It also shows another such mapping, but this one is not a function, since the rule does not assign the element x1 to the unique element of Y. As you can see on the function on the left, there's one arrow coming from X going to Y. Even though x3 and x4 go to the same Y value, that's okay. The problem we see is in the second one, where x1 has two arrows coming from it. That will not be a function. Now, this uniqueness of the range value is very important to us as we study function behavior. Knowing that f of 2 will equal 8 tells us something about f. And that understanding will be contradicted if we were to discover later that f of 2 also equals 4. That is why you'll never see a function defined by an ambiguous formula like f of x equals 3x plus or minus 2. Now remember, they're not zeros of the function or solutions. This is actually the function. Now in example 1, determine whether the formula determines y as a function of x. Well, what we're going to have to do here, is simple. Well, can we basically change y into f of x? In this case, we say yes, f of x equals x squared. And you should know by now that x squared is a parabola. It is a quadratic formula, or quadratic, so therefore it will be a function. Now if we look at B, we can change this function into y equals 12 minus x. So since we can do that, your answer will be yes, f of x will be 12 minus x. Now the ones that won't be functions are if you have a y squared, or square root of y, something of that nature. That will tell you it's not going to be a function. Now, another useful way to look at functions is graphically. The graph of the function y equals f of x is a set of all points x f of x, remember f of x is y, in the domain of f. We match the domain values along the x-axis with their range values along the y-axis to get the ordered pair that yield the graph of y equals f of x. Now in example 2, of the three graphs shown, which is not the graph of a function? How can you tell? Well, that's actually pretty simple. In the first one, in letter A, there is a unique x for every y. Correction, there's a unique y for every x value. Same with the second function. However, if we look at the third function, there's a value here for x equals 0, a value here for x equals 0, and a value here for x equals 0. So this is the one that is not a function. Now, a graph in the xy plane defines y as a function of x if and only if no vertical line intersects the graph in more than one point. Now we can see that again here. If we do a vertical line here, we can show you that we can move this vertical line anywhere on the graph, and it's only going to touch the graph at most one point. Same thing here. It'll only touch the graph in one point. Now, if we move it here, we're good here, but where we have issues starts here. You can see the vertical line, the graph will fail the vertical line test, showing you it's not a function. We'll usually define functions algebraically, giving the rule explicitly in terms of the domain. The rule, however, does not tell the complete story without some consideration of what the domain actually is. For example, we can define the volume of a sphere as a function of its radius by the formula v of r, so the volume of the radius, that would equal 4/3 times pi r cubed. This formula is defined for all real numbers, but the volume function is not defined for negative values of r. So if our intention were to study the volume function, we'd have to restrict the domain to be greater than or equal to 0. So we'd have to have the radius greater than or equal to 0. Now we do have an agreement here. Unless we are dealing with a model like volume or area that necessitates a restricted domain, we will assume that the domain of a function defined by an algebraic expression is the same as the domain of the algebraic expression, which is the implied domain. For models, we'll use a domain that fits the situation, which is the relevant domain. So for the volume problem, the relevant domain would be r greater than or equal to 0. Now, example 3, find the domain of each function. Well, here's what we do. I know, in example A, I know that the square root, you cannot take the square root of a negative number. So I know that x plus 3 has to be greater than or equal to 0. So because of that, that means x has to be greater than or equal to negative 3. Now, in interval notation, I can have this, which is what you should be familiar with, section 1.1. Now, for set builder notation, I'd write something like this. Do a curly bracket or a brace, x such that x is greater than or equal to negative 3 for all values of x in the set of real numbers. You'll see this again and again and again once you get to higher level mathematics into calculus. This is known as set builder notation. Now, if you look at B, we know from here that x has to be greater than or equal to 0. From the bottom, x cannot equal 5 because x minus 5 cannot equal 0, therefore x cannot equal 5. So now, our domain will be like this, because it's got to be greater than or equal to 0. Our interval notation, 0 to 5, not including 5, in union with 5 to infinity. That's interval notation. Now, set builder notation will go like this. Curly bracket, x such that x has to be greater than or equal to 0, x cannot equal 5, and then to save room here, x is an element of the real numbers. Now moving on to part C, it says a of s equals the square root of 3 over 4 times s squared. Now really, because it's just s squared, we're squaring the s, there's no value that it cannot be. So my domain, so negative infinity to infinity will be my domain. To put this in set builder notation, you go like this. Domain x such that x is an element of the reals. X can be any number. Actually, it says x here. I should be correct. And I should use s, just so used to using x. Now, finding the range of a function algebraic is often much harder than finding the domain, although graphically the things we look for are similar. To find the domain, we look for all x coordinates and corresponding points on the graph. And to find the range, we look for all the y coordinates and corresponding points on the graph. A good approach is to use the graphical and algebraic approaches simultaneously, as we'll show in example 4. Now in this case, find the range of the function. Well, because we have this, we know x cannot equal 0, and we know y equals 0 will be the horizontal asymptote. Therefore, y cannot equal 0. So my range will be y such that y cannot equal 0, where y is an element of the reals. Also in interval notation, negative infinity to 0 and union with 0 to infinity. Now we're going to put this on our calculator. You can see it pretty quickly and easily. If we did 2 divided by x, you can see, because the left part of the x-axis and the right part of the x-axis got a little more bold, that just means the graph is getting closer and closer to the x-axis and not touching it. Therefore, y equals 0 will be a horizontal asymptote. We'll get into more of that a little later. As you can see, the range then, the range will not include the y value of 0, which is the x-axis. The domain in this case will be the same thing as the range, negative infinity to 0 and union with 0 to infinity. And again, we're not including those because we don't want it to touch 0. Now, if you look at B, we have 10 minus x squared. Well, what this is going to look like, this is really going to be a quadratic opening down, shifted up 10. We know it's a quadratic equation because of the x squared. We know it's going to open down because of the negative x squared. The plus 10 will shift it up on the y-axis 10 spots. So there we have it. That means our range will go from negative infinity to positive 10. If we put this in set builder notation, y such that y has to be less than or equal to 10. Y is an element of the reals. In interval notation, you write negative infinity to 10, including 10. Now you can see that this is considerably more involved than finding a domain. We are hampered at this point by not having many tools with which to analyze function behavior. One of the most important properties of the majority of functions that model real-world behavior is that they are continuous. Graphically speaking, a function is continuous at a point if the graph does not come apart at that point. We can illustrate the concept with a few graphs. The one on the left here is continuous at all x. That means when you graph it, you do not have to lift up your pencil to draw it. Now, if you look at the second one, removable discontinuity, there's a hole in the graph. In this case here, we'll have f of a above where it would be on the graph. In the next one, which is also removable discontinuity, there is no value at f of a. Now, for the next one with jump discontinuity, the graph physically jumps from one part of the graph to the other with a large hole in the graph, a large break in the graph. And then for the last one, we have infinite discontinuity. Infinite discontinuity, one of the parts of the graph will go to infinity, the other will go to negative infinity, and in some cases, they'll both go to positive infinity. Now let's look at them individually. This graph here on the left is continuous everywhere. Notice that the graph has no breaks. This means that if we're studying the behavior of the function f for x values close to any particular number, we can be assured that the values of the function will be close to the value of f of a. Now, the graph next to it, the removable discontinuity, is continuous everywhere except for the hole at x equals a. If we're studying the behavior of this function for function f for x values close to a, we cannot be assured that the f of x values will be close to f of a, because it could have a value like it does here, it could have a value like it does in the second one, or it could not have any value at all. In this case, f of x is smaller than f of a for x near a. This is called a removable discontinuity because it can be patched by redefining f of a so as to plug the hole. Now, one way, as you can see in the graph there, you can draw it by adding a circle where that hole is. Generally, on your grapher, you will not see a hole like that. It'll look just like it's there, so you have to be careful. Now, the graph on the left here does also have removable discontinuity at x equals a. If we're studying the behavior of this function f for x values close to a, we're still not assured that f of x values will be close to f of a, because in this case, f of a doesn't even exist. It is removable because we could define f of a in such a way as to plug the hole and make f continuous at a. Then again, we have jump discontinuity. It is a jump discontinuity here in the middle graph because there's more than just a hole at x equals a. There's a jump in the function values that make the gap impossible to plug with a single point, no matter how hard we try to redefine f of a. And the last one there, it's a function with infinite discontinuity. It is definitely not removable, or a jump discontinuity, that's why it's infinite. Now, the simple geometric concept of an unbroken graph at a point is one of those visual notions that is extremely difficult to communicate accurately in the language of algebra. The key concept from the picture seems to be that we want the point f of x to slide smoothly onto the point f of a without missing it from either direction. This merely requires f of x approach f of a as a limit as x approaches a. A function f is continuous at x of a, or x equals a, if the limit of f of x equals f of a as x approaches a. I know this all sounds very difficult and it's probably mumbled up. I'm going to try and explain it very carefully in example 5. Also, a function f is discontinuous at x equals a if it is not continuous. Simple enough. So it's not continuous, it would be considered discontinuous. Now on example A, or example 5, graph the function and tell whether or not it has a point of discontinuity at x equals 0. If there is a discontinuity, tell whether it is removable or not removable. really there. Can you tell if there's a discontinuity? Probably not. The easiest way to do this, let's see if we can factor this out. So we can say h of x, I can take out an x on top, we love x squared plus 1 over x. We know from our original function, x cannot equal 0 because you cannot divide by 0. Therefore, this x and this x go away. So that means h of x will equal x squared plus 1. But remember, x cannot equal 0. So there is a removable discontinuity at x equals 0. And I'll show that on the graph in just a moment. Now you can see that on the graph by using your trace button. Okay? If you press trace, and I went to the left first, now I'm going to go to the right, you can see that there's going to be a removable discontinuity there because at x equals 0, there is no y value. Even if you go to the right, again, we'll have a y value again. So therefore, you can tell it's going to be a removable discontinuity at x equals 0. Now for part B, we're going to have here f of x equals the absolute value of x divided by x. What's our f then? So I have the absolute value of x divided by x. You can see here that there is going to be a discontinuity at x equals 0. So what we have, because there is a discontinuity, this will be, in fact, a jump discontinuity at x equals 0. You can see that there's going to be no number that you can plug in there to satisfy the equation f of x. Again, if you should have any questions about discontinuity or continuity or any of the other topics discussed in this video, please let me know.